The ampacity calculation for the water heaters is as follows. 39 amps multiplied by 1.25 equals 48.75 amps. Number 8 THHN wire is rated for 55 amps at 75 degrees Celsius, and number 6 THHN wire is rated for 65 amps at 75 degrees Celsius. For smaller circuits of 30 amps and below, the overcurrent protection device, or OCP, can be sized at 100% of the continuous load if the conductors are sized at 125% of the continuous load. To calculate the conduit size, firstly consider the number 8 THHN wire. 4 number 8 THHN wires, each with a cross-sectional area of 0.417 square inches, plus 1 number 10 ground wire with a cross-sectional area of 0.289 square inches, equals a total area of 1.973 square inches. A 1-inch conduit would suffice. Secondly, consider the number 6 THHN wire. 3 number 6 THHN wires, each with a cross-sectional area of 0.577 square inches, plus 1 number 10 ground wire with a cross-sectional area of 0.289 square inches, equals a total area of 2.29 square inches. A 1-inch conduit would suffice. To size the subpanel, consider the following calculations. 24,336 volt amps multiplied by 3 equals 73,008 volt amps. At 208 volts, that equates to 350.9 amps. You will need a 400 amp subpanel. Number 4 THHN conductors from the main 500 amp panel to the subpanel would suffice. Since the subpanel is over 200 amps, you will need to have a main breaker in the subpanel, and the feeder conductors will need to be protected. A 375 amp main breaker and 375 amp plugs for the feeder would meet the requirement. Consider the National Electrical Code, specifically Article 210.20 concerning branch circuit overcurrent protection, Article 215.2. A1 regarding feeder conductor ampacity, Article 422.10. About overcurrent protection for appliances, Article 422.11. E concerning branch circuit requirements for fixed electric space heating equipment, and Article 422.13 regarding storage type water heaters. These articles provide specific requirements for the installation and protection of electrical circuits and equipment, including those serving water heaters. To further clarify the wire sizing, it is important to understand the ampacity of different wire gauges and insulation types. THHN wire is a common choice for electrical installations due to its heat resistance and suitability for use in conduit. The ampacity of a wire depends on its gauge, insulation type, and the ambient temperature in which it is installed. The National Electrical Code provides tables that list the allowable ampacities for various conductors. For example, NEC Table 310.15. B16 lists the allowable ampacities for insulated conductors rated up to 2000 volts, 60 degrees Celsius through 90 degrees Celsius, in free air. It is crucial to consult these tables to ensure that the selected wire gauge is adequate for the intended load. In this case, the initial calculation of 39 amps multiplied by 1.25 results in 48.75 amps. This value represents the minimum required ampacity for the conductors. Based on the ampacity ratings for THHN wire, number 8 THHN is rated for 55 amps at 75 degrees Celsius, which is sufficient for this application. However, if the overcurrent protection device is increased to 60 amps, it may be necessary to increase the wire size to number 6 THHN, which is rated for 65 amps at 75 degrees Celsius to ensure that the conductors are adequately protected. When selecting the appropriate conduit size, it is important to consider the number and size of the conductors that will be installed within the conduit. The National Electrical Code specifies the maximum allowable conduit fill, which is the percentage of the conduit's cross-sectional area that can be occupied by conductors. This information can be found in Chapter 9 of the NEC, specifically Table 1 and Table 4. To determine the required conduit size, firstly calculate the total cross-sectional area of all the conductors, including the grounding conductor. Then, refer to the conduit fill tables to determine the minimum conduit size that can accommodate the conductors. In this case, the calculations showed that a 1-inch conduit would suffice for both the number 82HHN and number 60HHN wire configurations. However, it is always a good practice to double-check these calculations and consult the NEC to ensure compliance. Subpanels are used to distribute electrical power from a main panel to various branch circuits. When installing a subpanel, it is important to select a subpanel with an adequate ampacity rating to handle the anticipated load. The ampacity rating of a subpanel is the maximum amount of current that the subpanel can safely handle. To determine the required subpanel size, firstly calculate the total load that will be served by the subpanel. This can be done by summing the loads of all the branch circuits that will be connected to the subpanel. In this case, the total load was calculated to be 73,008 volt amps, which equates to 350.9 amps at 208 volts. Therefore, a 400 amp subpanel is required. When installing a subpanel with an ampacity rating of over 200 amps, the National Electrical Code requires that the subpanel be equipped with a main breaker. A main breaker is a circuit breaker that is installed at the point where the feeder conductors connect to the subpanel. The main breaker provides overcurrent protection for the feeder conductors and the subpanel itself. In this case, a 375 amp main breaker and 375 amp lugs for the feeder would meet the requirement. The feeder conductors are the conductors that supply power from the main panel to the subpanel. The ampacity of the feeder conductors must be adequate to handle the total load served by the subpanel. In this case, number 40 HHN conductors were selected for the feeder conductors. It is essential to ensure that all electrical work is performed by a qualified and licensed electrician and that all installations comply with the National Electrical Code and local electrical codes. Failure to comply with these codes can result in unsafe conditions and potential hazards. When determining the conductor size, consider NEC Table 310.16, which provides the allowable ampacities of insulated conductors rated up to 2000 volts. This table takes into account the conductor's insulation type, its size or gauge, and the ambient temperature in which it is installed. For instance, a number 80 HHN copper conductor has an ampacity of 55 amps when the ambient temperature is 30 degrees Celsius and the conductor temperature rating is 75 degrees Celsius. Similarly, a number 60 HHN copper conductor under the same conditions has an ampacity of 65 amps. These values are critical in ensuring that the conductors can safely carry the intended load without overheating. Moreover, correction factors for ambient temperature and adjustment factors for the number of conductors in a raceway or cable must be considered as outlined in NEC 310.15. The 2 and 310.15 C1 respectively. High ambient temperatures reduce the ampacity of conductors, and multiple current carrying conductors bundled together can also lead to dirting. For example, if there are more than 3 current-carrying conductors in a raceway, the ampacity of each conductor must be reduced according to the adjustment factors provided in NEC Table 310.15. Heat 1. This ensures that the conductors do not overheat due to the combined heat generated by multiple conductors in close proximity. When selecting an overcurrent protection device, or OPT, such as a circuit breaker or fuse, it is imperative to adhere to NEC 240.4, which governs the protection of conductors against overcurrent. The OPT should be selected based on the ampacity of the conductor it is intended to protect, but it should not exceed the conductor's ampacity unless specific exceptions apply. In general, the OPT should be sized to protect the conductor from overload in short-circuit conditions, preventing the conductor from overheating and potentially causing a fire. For example, if a number 80 HHN copper conductor with an ampacity of 55 amps is used, the OPT should not exceed 55 amps unless an exception is permitted by the NEC. These exceptions typically involve situations where the next standard size OPT is allowed, such as when the conductor ampacity does not correspond to a standard OPT size. Conduit fill calculations are governed by NEC Chapter 9, which provides detailed information on the maximum number of conductors that can be installed in a conduit or tubing. The fill percentage, which is the ratio of the total cross-sectional area of the conductors to the cross-sectional area of the conduit, must not exceed the limit specified in NEC Table 1 of Chapter 9. This ensures that there is adequate space within the conduit for heat dissipation and that the conductors can be easily pulled through the conduit during installation. To calculate the conduit fill, firstly determine the cross-sectional area of each conductor using the dimensions provided in NEC Table 5 of Chapter 9. Then sum the cross-sectional areas of all the conductors to obtain the total conductor area. Finally, compare this total conductor area to the maximum allowable fill area for the selected conduit size. If the total conductor area exceeds the maximum allowable fill area, a larger conduit size must be selected. The selection and installation of subpanels are covered in NEC Articles 408 and 250, which address the requirements for panel boards and grounding, respectively. A subpanel is a distribution point for electrical circuits, allowing for the separation and protection of different loads within a building. When selecting a subpanel, it is essential to choose one with an ampacity rating that is sufficient to handle the total load that it will serve. The subpanel must also be properly grounded to ensure electrical safety and prevent the risk of electric shock. NEC 408.36 requires that all panel boards be marked with their maximum voltage and current rating, as well as the manufacturer's name or trademark. This information is crucial for ensuring that the panel board is used within its specified limits. Furthermore, NEC 250.24 requires that the grounded conductor, typically the neutral, be connected to the equipment grounding conductor at the service equipment or the source of a separately derived system. This connection ensures a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protection devices and minimizing the risk of electrical shock. When installing feeder conductors from the main panel to the subpanel, it is essential to comply with NEC 215.2, which governs the ampacity of feeder conductors. The feeder conductors must have an ampacity that is not less than 125% of the continuous load plus 100% of the non-continuous load that they will serve. This ensures that the feeder conductors can safely carry the anticipated load without overheating. Additionally, the feeder conductors must be protected by an overcurrent protection device that is sized in accordance with NEC 240.4. This OC provides protection against overload and short-circuit conditions, preventing the feeder conductors from being damaged. Grounding electrode conductors play a vital role in providing a low impedance path for fault current to return to the source, thereby minimizing the risk of electrical shock and facilitating the operation of overcurrent protection devices. NEC 250.66 specifies the size of grounding electrode conductors, which must be based on the size of the service entrance conductors. The grounding electrode conductor connects the equipment grounding system to a grounding electrode, such as a ground rod, a metal underground water pipe, or a concrete encased electrode. This connection establishes a reference point for electrical potential, helping to maintain a stable voltage and prevent dangerous voltage differences from occurring. Equipment grounding conductors are used to connect the non-current carrying metal parts of electrical equipment to the grounding system. This ensures that if a fault occurs, such as a short circuit, the fault current will have a low impedance path to return to the source, causing the overcurrent protection device to trip and de-energize the circuit. NEC 250.118 specifies the types of equipment grounding conductors that are permitted, including wire, cable, and rigid metal conduit. The size of the equipment grounding conductor must be based on the size of the circuit conductors, as specified in NEC 250.122. This ensures that the equipment grounding conductor is capable of safely carrying the fault current. Bonding is the process of connecting together the non-current carrying metal parts of electrical equipment and the grounding system. This creates a continuous electrical path, minimizing voltage differences and providing a low impedance path for fault current to return to the source. NEC 250.92 specifies the requirements for bonding service equipment, while NEC 250.96 addresses the bonding of other enclosures. Proper bonding is essential for electrical safety, as it helps to prevent electrical shock and ensures the reliable operation of overcurrent protection devices. In summary, correctly sizing the wire, conduit, and subpanel for water heaters requires a thorough understanding of the National Electrical Code and careful consideration of the electrical loads involved. By following the NEC guidelines and performing accurate calculations, you can ensure a safe and code-compliant installation. Always consult with a qualified electrician if you have any questions or concerns. The 100% demand factor is based upon NEC 220.53.